So let's talk about the difference between facts, theories, and laws, right? This is one of those concepts that I feel like comes up all the time, and there's just a surprising amount of confusion that can go with it at times. So let's get to the bottom of it. First and foremost, keep in mind, we are talking about a hypothesis, where we're talking about a theory, where we're talking about a fact, when we're talking about a law, any of those things. The big trick is to first and foremost make sure we are talking about the same definition for each of these things, right? Because if you're talking to a friend and you say something like, oh, that's your hypothesis, or oh, that's your theory, we're probably not talking about the scientific use of those terms, and that's fine. We just have to make sure that when we are talking about them scientifically, they take on a very specific meaning. Now, we've already talked a little bit about a hypothesis and a null hypothesis, and so if you want to learn more about either of those two things, check out the experimental design video. But just long story short, remember that a hypothesis is really just what you are expecting is going to happen in an experiment based on prior knowledge and research, and it needs to be something that is testable. It's kind of a starting point once you get past that observing a problem point, right? And I always kind of caution to be a little careful here in my terms off the side where it says if your hypothesis proves correct, it's called a theory. That's a little bit of an overstatement. Really, you could probably say it more from the standpoint if your experiment is something that is repeatable, has been tested, has been shown to be accurate, possibly even peer-reviewed by other scientists. You're at least on the road to getting to a theory, right? And so, strictly speaking, it's not that you do an experiment on a hypothesis and if it's proven that you automatically have a theory. But if you think of it from the standpoint of we have this hypothesis and we test it a whole lot, we peer review it, we have other individuals test it, and we eventually can get ourselves to this point where we have this more uniting concept that we're going to call a theory, right? And so a well-substantiated explanation based on experimentation is really what a lot of times you'll hear discussed when talking about a theory. And really one of the big things to keep in mind is that a theory is the best explanation that we have based on the science at this given time, right? And so it's not something that is has a lot of questions that are still circling around it. It's something that we have tested. It is something that we have concluded upon. It is something that we've retested and peer reviewed and had other individuals run the tests. And when it all comes down to it, the theory is our best explanation at this point. So if you hear someone say, well, that's just a theory, keep in mind they're basically saying, well, that's just the thing that all of the data points to, that all of the research points to. It is our best explanation, and it should be widely accepted in the scientific society, the scientific peer review world, right? I want to make sure I explain the idea that it is not a fact. Okay, when we talk about facts, depending upon the definition that you use, sometimes facts can be used for an observation, like you observe that the plant is sitting in the room and you call that a fact. And if that's your definition of a fact, great, go with it. But if your definition of a fact is kind of the classic definition, where it's something that is absolutely true and something that has no room for questioning, then that is by no means a theory, because a theory can always be revisited. It can always be tested again. If new data or new technologies comes up, then the expectation in the scientific world is that we will take that technology, take that new research, and we will look at it through that theory's lens, and maybe even do more experiments, and it might have to change the theory, right? Whereas a fact is something that can't be questioned and can't be changed. And I always tell my students that a fact is really something that's very dangerous in the scientific society. I go a step further and say, truthfully, if that's the definition of fact that you are using, we shouldn't have fact in science, because there is nothing that is above the concept of questioning. If some new research comes out, some new technology comes out, and it causes us to revisit a theory, then that's exactly what we are supposed to do. That's what allows us to be open-minded and skeptical and scientific learners. We are not going to accept anything just because it's the way it always was. We want to do those tests. We want to ask those questions. And like I said, if it means we have to go back and change a theory, we will do that. Because in science, scientists are skeptics. We want to be able to question anything, especially if it's something that has new research coming out, new technology that we could maybe use to see things we haven't seen before. And so I always tell my students, stay away from that word fact anywhere you can, and just focus on that theory, right? The theory is the best explanation we have, widely accepted, and it has awesome value in the scientific and social world. And just kind of going a step further, just to get across my point about this whole idea of how dangerous it can be if we talk about something being a fact or something being unquestionable. One of the longest running scientific facts, if you go way back to the days of Galileo, was that the Earth was the center of the universe, something we call a geocentric universe. And so geocentric just means Earth-centered, right? It used to be the idea, be it from various theological texts and whatnot, that the Earth was the center of the universe and that everything, the moon, the sun, all the planets, all rotated around the Earth. And you might say, like, yeah, that obviously that's something that has been proven incorrect at this point. However, if you think back to the days of Galileo, that when those scientists did the research and actually found that things like, Venus was changing phases as it circled the sun with the Earth, and it was not changing phases in the way you'd expect if it wasn't, orbiting around the Earth. When people like Galileo came out with that scientific evidence, rather than the scientific community being super impressed and, changing the textbooks and saying like, wow, that's fantastic. Great job figuring that out. In so many situations, we locked up the scientists and we threw away the keys, sometimes even worse, honestly. And so it just gets back to that idea that everything in science should be questionable. It's okay to be questionable. In fact, realistically speaking, we want scientists to ask questions when they come across something that doesn't make sense. That's how science gets better. That's how theories get stronger. And that's how this process becomes a trustworthy process. And I would argue that science is a very trustworthy process because of that peer review, because of that peer scrutiny, and that willingness to listen to new information when it becomes present. And it's also important to make sure that when we're doing that we're bringing society along, right? One of the things that is an unfortunate truth of this day and age is that we have a lot of individuals that are just okay with thinking that the scientific process isn't trustworthy, or they might be okay with a medication to treat a disease, but as soon as something comes out from a scientific study that they don't agree with or it doesn't support their own bias, they want to just chalk it up to the idea that, oh, sometimes science is lying or it's wrong. And that's really something that it's unfortunate to the process of science, because the actual process of science, where we're doing experiments, we're collecting data, we're hopefully publishing that data and having the peer review process in journals, it's a very cutthroat process that really ends with us getting our hands on the best information available, be it whether that's something like we're testing medications, or we're testing things like vaccines, or we're testing things like, the theories that build the scientific process, like the central dogmas of genetics and biology. Realistically, those are all theories that are growing and getting better all the time. And it is our job as the scientists to also make sure that we're helping society understand, so that we're not closing minds, that instead we're making this trustworthy process where questioning's okay, and where a theory can change based on new research. Also, guys, remember that if science is done properly, that it should be always tied to a concept that falls back to natural reasoning, right? And natural reasoning is just the sciencey term that means it's something that you can observe using the five senses, right? You can touch it, taste it, see it, smell it, hear it. It's just one of those things that you can actually do the experiment. You can collect that data, and from that data, you are able to then put information out there that can be used by both science and society. Because, you can see something online, or you can read something that has, graphs and data and maybe AI generated images that can actually make it look like something that you observed is an actual scientific observation. But remember, there's a major difference. There's a big difference between when you are making an observation of a natural phenomena, or when you are observing or listening to or reading about someone else's observation. The big trick here to remember is that when I'm looking at someone else's observation, that doesn't mean it's wrong. It doesn't mean it's not trustworthy, but it does mean it requires a degree of scrutiny where I'm going to, if I have some questions or I have some concerns, that I'm going to maybe dig a little deeper and look for additional supporting research, right? Doesn't mean we can't trust anything, right? I feel like we have this really bad habit right now of just making it sound like, thanks to things like AI, that we just can't trust anything we see or read on the internet. And that's not true. That's technically being a cynical viewpoint in itself. But it does mean that we just have to be a little bit more careful when we're being a skeptic, right? We need to make sure that if something seems a little outside of what we are expecting, that maybe it means we need to do a little bit more research. Or in some cases, maybe it means we need to go do some of our own testing, our own experimentation, which I know sounds crazy to think. Like, what do you mean go and do my own research? But in some circles, in some parts of the scientific field, that's how it works. If we hear of a medication that just seems too good to be true, it then becomes the responsibility of the pharmaceutical science world to see whether or not that is actually too good to be true, or whether it's, some fantastic phenomena that's going to change the world, right? And we've seen it go both directions, right? Support. Law is very similar in concept, but again, it's not a fact. It's still something that can change. It is still something that new research could come out and it changes how we understand it, or maybe in what realms the law applies. So like, the laws of gravity, right? It turns out it looks a little different depending on what planet you're on, right? And that's okay. That doesn't make it not a law. It just means that it's going to fit into certain criteria, right? So I always think of it like a law is going to be the thing that describes how something is occurring in a scientific process, not necessarily the why it happens. That's going to be more the job of a theory. And so when we're trying to figure out like why evolution happens the way it does, there's a lot that goes into that, right? So it turns out the evolutionary theory is enormous, right? But if we're just specifically talking about like how it's happening, then maybe from the standpoint of evolution, we're going to talk about something called the Hardy-Weinberg principle, where we can actually show, allele frequency, gene frequency changes in populations and set it up a nice mathematical equation. And we can actually show how a population's changing over time. That's a very useful piece of information. It is a law that we can use to show evolutionary change. But it doesn't tell me how, right? That's still where the research comes in and the theory comes in. And so as a general rule, laws are usually going to give you some sort of an equation to use here. And that equation is going to be something that is going to specifically be describing how something is happening. So if you change the mass of something, how does that change the acceleration? It's telling you specifically how the parts of the experiment or the variables in the experiment are going to change the end result. But if you're looking for why something is happening, that's where you get into the concepts of the theories and the hypotheses and the experiments and all that good stuff, right? So they are all related to each other. They all have their jobs in this process, but just keep in mind they are not the same thing. And so you just sometimes have to ask yourself the question, are you looking for how it's happening and how the variables might change how it occurs? Or are you asking why it's happening? And if that's the case, now you're looking to the theory and how the theory explains that why.